What's going on, smart people? I put out a poll. Do you guys want to see a video on the derivation of the Dirac equation or another episode of tensor calculus? I think you guys might be tensor calculus out because you voted for the Dirac equation. You want a Dirac and roll, that's understandable. But you're not out of the woods like that because, yeah, we're not going to be focusing much on tensors today. But the Dirac equation, it's a relativistic theory of the electron and other spin 1/2 particles. If it's relativistic, the best way to communicate that kind of thing is in the language of 4 vectors. So we're not going to be talking about tensors today, but we should spend a little bit of time going over 4 vectors because we're going to be doing contractions and things like that throughout the video. So I want to take a little bit of time going over some 4 vector stuff before we get into the nitty-gritty. 4 vector stuff. Say that we have some 4 vector, I'll call it p mu. And I want to find the dot product. I want to do p mu dot p mu. How do I do that? We're kind of going to breeze through this a little bit because I do have an entire video on taking dot products of 4 vectors. But effectively, we want to employ the Einstein summation convention. Einstein summation convention says that we sum over repeated indices so long as one is upstairs and one is downstairs. So we can do the dot product, we can perform the contraction if we can do this. So if p mu is just some p0th component and then maybe a px, py, pz, that's a z, which is equal to, say, p0 and then p vector. What is it with downstairs indices? Well, if we want to write a contravariant vector downstairs instead, we can do that by applying the metric tensor. So we can define p mu equal to g mu nu p nu. So we're summing over this upper index, and then all that leaves is something with a lower index. Now, what does that mean? The reason I'm doing this is because when we take dot products of 4 vectors, there's going to be this relative minus sign, and if you haven't done a contraction of 2 4 vectors before, that might seem like it comes out of nowhere. Now, our metric tensor is just going to be the Minkowski metric, and we're going to be using the plus minus 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 convention, so 1, 0, minus 1, minus 1, minus 1, and 0. So implicitly in our contraction of p mu, we really have that it's saying p mu, which is g mu nu p nu p mu. So this is what we're really doing. So when we take the dot product in, say, Cartesian coordinates, we're doing the exact same thing, but it's a trivial thing to write out, and it's kind of unnecessary because our metric in Cartesian coordinates is just going to be a diagonal of 1s. That's why our dot product in Cartesian coordinates is positive definite. But if we're working in a Minkowski space, we have the relative minus signs between time and space. So when we do this, when we apply g mu nu to this upper index, to this contravariant vector, only the diagonal terms survive. So the first one is going to be g0, 0, p0 plus g0, nope, g11, p1 plus dot dot dot. The first term gets a 1, so that's still p0. But the spatial bits all get this relative minus sign, minus our px, minus our py, and so on. So it's py dot dot dot. So this is going to give us a minus, or it's going to give us a p minus p vector. Okay, so that's where this minus is about to come in. So when we take the contraction of this vector with itself, what we get is it's going to be p0 squared, because the time bit is still positive, minus p squared, minus p dot p, or p vector dot p. So that's the crucial thing that we have to have down before getting into the Dirac equation, because we're going to be working with 4 vectors a lot. But that being said, let's talk about Einstein's relation. Everyone knows E equals mc squared. Really, the equation should be E equals mc squared-ish, because there's that extra term that we're about to write out. So Einstein's relation says that the energy squared, the square of the energy, is equal to mc squared squared plus the momentum, something proportional to the momentum squared, pc squared. I don't want to be writing out c's throughout the entire video, so what we're going to do is we're going to set c equal to 1. Now this is not me saying c is 1 meter per second. That's not what I'm doing. What I'm doing is saying, instead of saying c is 3 times 10 to the 8th meters per second, I will choose a new unit such that c is one of those units. So define the Dotson equal to 3 times 10 to the 8th meters per second. Then c is approximately 1 Dotson. So that's what I'm doing here. So if c equals 1, we can rewrite Einstein's relation equal to m squared plus p squared. Let's subtract this stuff over, and we get e squared minus p squared minus m squared is equal to 0. Now light bulb should be going off in your brain that says, oh, that's why you wanted to do a 4-vector, Andrew, because if we take the 4 momentum, which is equal to the energy and the regular momentum, keep in mind this is really an E over C, but C is 1, C is always 1, then if I contract it with itself, we just get an E squared minus P squared. So we can rewrite Einstein's relation as P mu, let's do P mu minus M squared equal to 0. Awesome. And if we just look at without the 4-vector notation, if we were to just quantize energy and momentum, they both become operators, as you do with regular quantum mechanics. Your classical observables become quantum operators. If we were to do that with this right now, we would just get the Klein-Gordon equation. I have a whole video on that, check that out if you're interested. But the Klein-Gordon equation has some benefits to it, right? It treats time and space on equal footing. The only problem is with the derivatives that it treats time and space equal on, it's second-order derivatives, which means that you can't really uniquely define the wave function with a single initial condition. That's fine, maybe that's not a huge deal. It also offers negative energy solutions. Fine, maybe that's not a huge deal. But because the probability density is proportional to the energy for this case, if you have negative energy, that means that you also have negative probability densities, which is actually a very big deal. That doesn't make sense. So there's some problems with the Klein-Gordon equation like that, not to mention it can only describe spin-zero particles, which are few and far between. So what the Dirac equation has going for it, which we'll get to, is it comes with a theory of spin 1/2 particles, which in your quantum mechanics courses, that's kind of all you treat anyways, which is really nice. So Dirac had the idea of factoring effectively the Klein-Gordon equation. Is there a way to factor this beast here and then go through the motions of promoting observables into operators? Well, let's see if we can do that. First things first, what can you not do if you want to factor this? If I want to factor this equation here, can I say something like, I don't know, P mu plus M, P mu minus M? Can I do that? If I multiply this out, well, that gives me that contraction. Maybe the minus terms. No, this doesn't work. The reason this doesn't work is because these are 4 vectors. These are not the vector components. These are the vectors themselves. So in a sense, what you would be trying to do here is you'd be trying to subtract a scalar from a vector. You can't do that. So if we want to be able to factor this, we've got to actually attach another maybe arbitrary 4 vector that we'll put limits on and constrain later. That way we can contract the 4 vectors to give a scalar. That's what's nice about working with 4 vectors, is when you contract them, you're guaranteed to get a Lorentz scalar. So instead of doing that, let's have 2 arbitrary, right now arbitrary 4 vectors that we're contracting these with. So we'll call those maybe alpha nu contracted with p nu plus m times gamma mu minus m. Nope, times the 4 vector p mu minus m. Okay, so we've got 4 vector, it gives us a scalar minus a scalar, so at least dimensionally, and this makes sense, and this should be equal to 0. So at the end of the day, we want to be able to multiply this out and recover this here. So let's go ahead and multiply out our factor, and we'll see what our alphas and gammas have to be in order for this to make sense. So if we multiply this out, we get alpha nu, gamma mu, p nu, p mu, and then the cross terms, so minus m alpha nu p nu plus m gamma mu p mu, and then the final term minus m squared, and this should be equal to 0. Well, right off the bat, we know that we need the cross terms to vanish, so we can already put a requirement on alpha and gamma. And the requirement should be that when these indices match, when nu and mu are equal, alpha mu should equal gamma mu. So if we multiply this stuff out, so if we have minus m alpha 0 p0 plus m gamma 0 p0, we can make these vanish by this requirement here. Okay, so all of these are going to be, they're going to be added up and cancel each other, which gets rid of these cross terms. Okay, so we made that requirement. And now we can just rewrite this equation as gamma nu, gamma mu, p nu, p mu, minus m squared is equal to 0. So just to recap what we've done here so far, in forcing alpha mu to equal gamma mu, we were able to get rid of the cross term. In doing that, all we're saying is that that alpha nu is really just a gamma nu, to make sure that that plus cross term cancels with the minus. So nothing crazy is actually going on here. And this is what we're left with now, and we need this somehow to reduce to this. So we need to recover a couple more conditions to place on this 4 vector here. So let's brute force our way through it. Let's just start summing over mu and nu and see if we can find something. So if we say, let's start at 0, gamma 0, gamma 0, p0, p0, plus gamma 0, gamma 1, p0, p1, plus gamma 0, gamma 2, p0, p2, plus gamma 0, gamma 3, p0, p3, plus gamma 1, gamma 0, p1, p0. See what I mean by brute forcing your way through this? This is gamma 2, gamma 0, p2, p0. This should have a, what am I doing? 3 here, sorry. Plus gamma 3, gamma 0, p3, p0, and we've also got our like terms, so we've got, plus gamma 1, p1, p1, plus gamma 2, p2, p2, plus dot dot dot, and then our minus m squared at the end. Now let's see if we can collect some terms. So we know that our diagonals are mu equal to nu. I always point at that and say mu. For mu equal to nu, we can just explicitly write that out as, say, gamma mu, p mu, kind of a sloppy notation, but I'm just saying that I'm summing over all of the same indices. So maybe explicitly I could just write sum over mu, just because that's normally not conventional to write this way. I'm just saying like with like. And then we have all of these cross terms, and is there any pattern to those? Well, we've got a gamma 0, gamma 1, p0, p1, gamma 1, gamma 0, p0, p1. These are just numbers, so it doesn't matter which order you multiply them in. So that's plus p0, p1, gamma 0, gamma 1, plus gamma 1, gamma 0. And the same thing happens for the other one. So we've got like a p0, p2, gamma 0, gamma 2, plus gamma 2, gamma 0, plus dot dot dot, minus our m squared. Now we're actually making really, really good progress. Now this is a weird way of writing this, and I'm going to also write it now in a weird way also, where instead of summing over mu with 4 indices that are the same, that just looks weird. I'm going to replace one with the nu, and then I'm going to sum over them for mu and nu equal to each other. So instead of writing this, I'm going to write this as a sum over mu and nu of gamma mu, gamma nu, p mu, p nu, but place the condition that mu has to equal nu. Okay, so we're not taking these off diagonal components. So that's a little bit nicer of a way of writing it, I think. Now, the next thing brings us to a very fascinating point of this whole derivation. We need these cross terms to cancel. Here we're summing over mu and nu, but mu equals nu, so we almost have this term here where we're summing over just the diagonal, we're summing over like equals like, but we need one of them to be upper. We'll get to that. But we need mu not equal to nu to go to 0. We don't want any of those terms. But we have all of these cross terms to deal with. And the only way that we can get these terms to cancel without forcing that the components of the form momentum be 0 themselves is that these terms must be 0. And if we look at this, it's 0, 1, 1, 0, 0, 2, 2, 0. That's just an anticommutator. So in a sense, what we need to enforce, another requirement that we have to say is that the anticommutator of gamma mu with gamma nu has to be 0 if mu doesn't equal nu. Or rather, for mu not equal to mu, because here the indices don't match. And that's fascinating to me, because if I was Dirac looking at this, I'm under the impression that I'm working with a 4-vector whose components are just numbers, and then they have to satisfy this anti-commutation relation. And normal numbers just don't do that. Maybe Grassmann variables do, but I'm saying a times b plus b times a has to equal 0, but a and b themselves aren't necessarily 0. Normal numbers don't do that. Matrices do. So this thing that we started out with, this 4-vector, it's still a 4-vector, yes, but its components are matrices, and that just blew my mind when I first found this out. So imposing that these components of our gamma 4-vector are matrices themselves, we call them the gamma matrices. Now we can actually get somewhere so that these go away. So our anticommutator forces that for mu not equal to nu, the anticommutator equals 0. And then here, we need this term, this one last surviving term, to sort of work as raising one of these indices. That way we can properly do a contraction. So in a sense what we need is we need to raise this nu upwards. We need to say, because we know that p mu is just equal to the metric tensor, the contravariant metric tensor, acting on the lower indices. So it just raises it up. Okay, so for mu equal to nu, we should just get the metric tensor effectively. So for g mu nu. Okay, and we can actually combine all of this into one anticommutator relation. So we can say that the anticommutator of gamma mu comma gamma nu is equal to 2 times the metric tensor. And let's make sure that this makes sense to us. So this is saying gamma mu gamma nu plus gamma nu gamma mu equals 2 g mu nu. Does that make sense? Well, we already know that the anticommutator for mu not equal to nu is 0. So that's already satisfied because mu not equal to nu for the metric tensor, those components are 0, at least in Minkowski space. So that works. So for mu not equal to nu, this works. And then for mu equal to nu, well, we've got mu equal to nu, so we've got gamma mu gamma nu plus gamma mu gamma nu. It doesn't even matter which order you add them because they're the same thing at this point. Well, that's just going to give us a factor of 2 times, I lost my eraser, which should be equal to 2 times the metric tensor. 2's cancel and we get our relationship that we needed right here. Great. So this perfectly defines what our algebra, what our relation between these gamma matrices have to be. Now let's put everything together and finally get our Dirac equation. We've earned it. Great, so we now know that we can factor our relation that we started with in terms of the gamma matrices. We don't have to worry about the indices matching up because the anticommutator relationships take care of those indices for us. And any matrix that satisfies this anticommutator relation, which is said to define the Clifford algebra, will work for the Dirac equation. The convention in physics is to build the gamma matrices in terms of the Pauli matrices. So this is going from 1, 2, and 3. And then the 0 with 1 is just in terms of the identity matrix. Great, so this whole thing is supposed to equal 0. And this whole thing can equal 0 if this is 0 or this is 0. The convention is to take the term with the minus m. So if we say gamma mu p mu minus m is equal to 0, yes, this is a 4-vector, but its components are the gamma matrices. Right, so this is technically a Lorentz scalar, but in reality it also has two extra what we call Dirac indices to specify the components of the matrix itself. So it's a Lorentz scalar, but if we multiply it out, you have gamma 0 AB, or alpha beta P0 plus 1 AB P1 plus dot 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 minus M. We've got a number times a square matrix, times a 4x4 square matrix, minus something that looks like a scalar. So for things to make sense dimensionally, you could think of just tacking on an identity matrix onto this mass term, since we're dealing with matrices minus this M. So that was confusing to me initially, so I figured I'd talk about that here. The last step in extracting the Dirac equation from all of this is to quantize the form momentum. Now we know that the contravariant, form momentum is in terms of the energy and the regular momentum. And we already know how to quantize this from quantum mechanics 1. This is just energy from the right-hand side of the Schrödinger equation becomes an I h bar times the time derivative, right? But let's set h bar equal to 1. So it's just I ddt. And the momentum goes to minus I times the gradient, where again h bar is set equal to 1. Then the quantized version of our contravariant form momentum is just I ddt minus del. Okay, and now if we lower it using the metric tensor, the spatial part gets a relative minus sign. Because remember, G mu nu P nu is equal to P mu. And that spatial part of the metric is going to tack on another minus sign. So P mu goes to I ddt times del, which we can just write as I d mu. So d0 is ddt, and then the spatial parts for mu greater than 0. And now all we have to do is substitute this in to our equation here, and we get I gamma mu d mu minus m. Now this is an operator now. Our observables are replaced with quantum operators. Operators really only make sense when they're acting on a function. So we have it act on our function. And since we're dealing with 4 components, this is a 4-component wave function, sometimes called a Dirac spinner. And this is equal to 0. And this is the famous Dirac equation. There's one other way that we can write this. And we're done now. I'm just going to show you another way that we can express this. Whenever we have something that is contracted with the gamma matrix, which happens quite a bit in quantum field theory. So if we have, say, some vector, we'll call it V, contracted with the gamma matrix, we shorthand this with a V slash. So put a slash to let us know that it's been contracted with the gamma matrix, because it's a pair that happens a lot. Shout out to all the pairs. So we can rewrite the Dirac equation using the slash notation to make it even shorter. It says that I d slash minus m acting on psi is equal to 0. And that is it, ladies and gentlemen. Maybe in a future video I'll get into interpreting the Dirac equation, and we'll talk about antimatter and these 4-component wave functions and all that good stuff. But I think this video is long enough as it is now. I hope you guys enjoyed the video. This is a fun thing to watch. Yeah, you must have had fun watching this. It was a fun thing to make. So let me know in the comment section if you enjoyed the video, and I will see you guys there.